Currently an assistant professor in the Department of Civil Engineering at McMaster University. Young? In my presentation, I'm going to talk about the two emerging technologies for the recovery of saline gradient chemicals. Just to explain the salinity gradient chemicals, let me start with the fresh water, salt water in a container. And they are separated by a membrane. And let's assume that this membrane is allowing only water transfer. It doesn't allow ionic transfer. Then what I'm going to do is to close the salt water chamber so that I can hold the pressure in the chamber. And then if I leave it a little bit, then there will be osmotic pressure building up at the membrane into the salt water chamber. And the total pressure, total osmotic pressure can be calculated by this simplification, delta CLP. And if you have typical seawater with 0.6 moles per liter of ions, then the osmotic pressure will be 15 atmospheres. A pressure of 15 atmospheres is equivalent to 150 meters of water head. So we have huge water pressure, and we can actually use this pressure to run an electricity generator to produce electricity. So this whole idea over here is that we generate 15 atmosphere of osmotic pressure, and then we use this pressure to produce electricity. And this idea, and this basic concept is called pressure retarded osmosis, or PRO. And there's another method, and in this method we use ion exchange membranes. So here we have anion exchange membrane and cation exchange membrane. So this anion exchange membrane allows only anionic transfer. It blocks cationic transfer. And same thing happening with the cation exchange membrane. And let's say we have salt water in between this membrane, and we have fresh water outside of these membranes. Then because of this concentration gradient, ions want to travel through the membrane, and they want to stay in fresh water, just like this. But because of this special selectivity of this membrane, this anion exchange membrane only allows anions. So anions can travel only to the left. And same thing happens over here. There is cationic transfer to the right. So basically what we have over here, we have positive charge transfer to the right and negative charge transfer to the left, which means we have electric current generation using the concentration difference between salt water and seawater. And let's have a look at the magnitude of the driving force for electric current. For typical seawater and river water, we basically assume about 0.1 volts per cation and anion exchange membrane pair. And one interesting thing is that if you have multiple pair of ion exchange membranes, like for example, let's say we have 3 ion exchange membrane pairs, then the resulting total voltage would be 0.3 volts. And if you have 1,000 pairs of ion exchange membranes, the voltage would be 100 volts. So the bottom line over here is that there's basically no limit in increasing the total voltage as long as we have sufficient amount of ion exchange membranes. And we still need one last step. The electric current in this stack of ion exchange membrane is driven by ionic flow. So we have to convert this flow of ion into the flow of electrons so that we can use it as electricity. So we use electrode and electrode reactions. For example, we have anode on the left-hand side and we have cathode. And at the anode, we drive oxidation reaction. For example, water oxidation into oxygen gas. And through this oxidation reaction, we gain electron. And on the other hand, at the cathode, we have water reduction reaction involving hydrogen gas. And we can dump electron to this reaction. So if we connect anode and cathode, we can generate electron flow, generating electricity. And this idea is called reverse electrodialysis, or RED. And I'm going to show some pilot-scale demonstrations. Doug showed this picture. In 2009, people in Norway built a 10 kilowatt PRO power plant. And this is a demonstrative stack of LED system. So it's difficult to see because it is covered, but behind the cover, there's 2 electrodes on the top and on the bottom, and they stack ion exchange membrane horizontally. And even with this pilot scale demonstration, there are no full-scale power plants using this technology. So to achieve the full-scale power generation using these technologies, there are some challenges. And let me start with the energy density of salinity gradient energy. So let's say we have 0.5 liter of seawater and 0.5 liter of fresh water. So we have 1 kilogram of water. And out of this salinity gradient, we can produce up to 1 kilojoule. So basically, energy density of the salinity gradient is 1 kilojoule per kilogram. And just for comparison, for typical fuels for electricity generation, we have huge amount of kind of energy density with these fuels. So the bottom line over here, the energy density is really low. So we have to have very high energy recovery. Otherwise, the energy we recover from this technology may be even smaller than the energy we consume for pumping. So here is the list of challenges. Like I mentioned, pumping cost is one of the challenges. And membrane resistance. We lose a certain amount of salinity gradient energy as we transport water through the membrane, as we transport ions through ion exchange membranes. Membrane fouling is one of the biggest problems in this system. And there's some energy losses in turbine generator and also through the electrical reactions. So I'm going to talk about, in the next few slides, I'm going to talk about a project that we performed to eliminate the energy losses by electrical reactions. And I have to mention that this project was performed at Penn State University under the guidance of Dr. Gustavo.
We'll see you on the football field.
Here's our RLD system, reverse electrolysis system. And we have water electrolysis reaction at the electrode. And these reactions consume 1.23 volts. And this is the theoretical minimum voltage we consume. So if you have a higher, if you have a practical system, and if you have higher electric current, the loss will be much greater than 1.23 volts. And let me talk about a new thing for a while. And this system is called micro-fuel cell. And micro-fuel cell can be used to recover energy from wastewater. So in this micro-fuel cell, we have a bioanode and air cathode. And at the bioanode, we have a special bacteria, or exoelectrogenic bacteria, and they oxidize organic matter in wastewater. And they dump electron to the bioanode. And at the cathode, we have oxygen reduction reaction. And these redox couple, or these electron reaction couple, are driven spontaneously, so that we can recover energy out of these reactions. So up to about 1 to 1 volt. So the idea, so what we did is to put these MFC anodes in our RLD system, so that we can basically convert the energy consumption for electrical reaction into energy recovery from the electrical reaction. And this is the reactor that we built in the lab. So it is a little difficult to see. There's bioanode on the left, and here's the stack of ion exchange membrane, and here is the air cathode. And the results were quite promising. Energy recovery goes up to 30 to 40% when you combine MFC and RLD. When you compare this with 9% with RLD only system, it is a substantial increase.